start the recording. Yeah. Yeah, right. Okay. Yeah. So let me share the presentation. Okay, so let me share. Okay. Okay, so can you see the slide? Hello?
Yes,
Hello?
sir.
Okay, good. Yeah, right. Yeah, I'm just keeping in slideshow mode. Yeah, right. Okay. So yeah, before the start of the lecture, so have any questions? Okay. And so yesterday I sent an email regarding the group wise splitting of the class strength. So the as on yesterday, I think it's mostly the strength was frozen. It's about 247. So I divided into 5 groups, like 50 each, where the last group contains the 47, and for each group I have assigned 2 TAs. So and their details, mobile number, and their Gmail address also shared and all. So please be in touch with them, and based on this one, where if it is related to the architecture part, then the corresponding TA you can contact him. If it is a OS part later on after the mid sem, then you may contact the other TA and all. Right, so please try to contact, be in touch with them for any queries, any type of queries and all, as a for that one. And for me, if you want to discuss and all, we can discuss at the beginning or at the end of the class and all. Okay, so so let's start the class from where we stopped in the last week. So in the last week, we are discussing about this set architecture. So in that, we discussed about different types of instructions and their formats and all. And we also discussed about in high level language, we are using various things like conditional operators, logical operators, and then the loops for iteration, and then sometimes we use the procedure calls, nothing but the calling the functions and all. So in that case, how these corresponding functions are translated or implemented in actual machine level, at a machine level instruction level, at a machine level instructions and all. So that we are discussing. So in that, we have mentioned that actually here, for calling a procedure, so these are the 6 steps that need to be followed, because when you call a procedure, the control transfer to the caller to the callee. It means that from where you are calling to a procedure where the procedure to be executed. So the control will move to, like, the program sequence will be like shifted from the current program to the procedure where you have called and all. And then for calling the time of calling a procedure, you need to pass some parameters depending on the procedure requirement or the function and all. So that's why place the parameters in the registers. That is nothing but what are the parameters you want to pass it to the procedure. You need to place it in appropriate registers and all. So those are known to be argument registers. And then afterwards, you have to transfer the control to the procedure. Then the procedure, execution of procedure should take place. That means acquire the storage space and perform the procedure operations. That means whatever the procedure execution has to take place. And once at the end of the procedure, the result has to be placed in the appropriate register so that the caller can see the result, right? And then after that, after you place the result in the register, designated register, then you need to return the control back to the caller from where you call the procedure and all. So these are the 6 standard steps in which you can able to call a procedure and you can execute and again back to the main program or the program from where you call the procedure and all. The same thing applies even for the repeated calls or the nested calls also. And here these are the various registers that are used when you are calling the procedures and all, or when you are making use of the procedure calls. Like this A0 to A3 registers, these are used for carrying the arguments or like for passing the arguments from procedure from main program to called procedure and all. So these registers are numbered with 4 to 7. And then for placing the results and all, you can use these 2 registers named as V0, V1, and they're numbered as 2 to 3. Because there are total 32 registers, 0 to 31. And in that, these numbers are meant for 4 to 7 are meant for argument registers, and V0 and V1 are meant for the returning the results. And T0 to T9 are the temporary registers, we know that. And the procedure calls can use these temporary registers directly by the local procedure and all, whichever you are executing currently. And for using these registers S0 to S7, so if you want to use these registers by a procedure, by a recent procedure, which you are going to execute, so in that case, actually, you have to save these registers before using them. That means the procedure, if it want to use this S0 to S7, then first of all, it has to store them, and then you can use that. And afterwards, whenever you are returning at that time, before returning, again, you need to like restore these values and all, so that the original procedure or original the main program can reuse those register values and all. And as I mentioned, these are the 4 registers. Like out of these, there are the 3 registers which maintains some specific address and all. We'll see that what are those addresses and what are the purpose of these addresses and all. And there is another register known to be return address RA, named as RA, and this is the number of this register is 31. Basically, this register is to maintain the return address. That means, suppose for example, from a main function call, you are calling some function to compute some of the array number, some of the array elements of some array. So in that, after computing the sum and all, then the sum will be returned. Then again, the program, that means the next instruction to be executed will be starting from a main program. So the address of this main program where the procedure has been called, that particular address will be stored in the specific address known to be RA, return address and all. So with that, after completion of the procedure, and the control will be returned back to the main program by using this particular address known to be return address. And these 3 addresses and all we will discuss. One is known to be stack pointer, and another is known to be global pointer, and other one is known to be frame pointer and all. And so this global pointer is nothing but, from the name here you can see that. So in a program there is some data which refers to the static data. They are the constants, or that is the data which is used by the entire main program, and that means the functions that are within that also you can use that particular data. That's not to be static data. It means that those variables or that particular data is visible to the entire the program and all. It's known to be static data. And the static data will be indexed, or the static data will be like pointed out or indexed by the global pointer and all. It's nothing but the global pointer is nothing but the address where this from with which you can able to access the static data and all. So it's just like the base address, the base register, which contains the address of the starting of the array. So with which, based on the offset, you can able to access the desired array location. The same way here also, the global pointer maintains the address around the middle of the static data, with which, with a positive or negative offset, it can able to access the static data, like either in the upside or the downside. And we'll see that actually how it will be. It's just like a base register With that, you can able to, by using offset, you can able to access the desired static data points, the static data values and all. And then the stack pointer is nothing but, we'll see that whenever you call a procedure and all, the data related to the local procedures, the local procedure, so that thing that will be maintained, that will be placed in the, that will be placed by using the stack pointer and all. The stack pointer is nothing but, suppose you are calling a local procedure some, and in that actually you are using some array or some data elements or some local variables and all. So all those data elements will be placed by using a stack pointer. And that means every time you give it, you provide the space by using a stack pointer, by decrementing the stack pointer, and then you are loading the desired values into the stack and all. And then the frame pointer is also used along with the stack to index the different values that are used by the local procedure and all. We'll see that why the frame pointer is again required and all, because as I mentioned that the stack pointer is used to create the space for placing the local variables or the local data for a given procedure and all. Then in that case, then what is the use of FP, that we'll see that we can see how it can be used and all. So these are the various entities that are used when you are dealing with the procedure calls and all. Yeah, and another thing is that actually when you're calling a procedure, it means that you are shifting the, or you are changing the control from a main program to some other location where the procedure is placed or where the procedure is available. So for that, the MIPS instruction that is used for transferring the control or for jumping to the procedure call for execution. So that will be done by using instruction known to be JAL, JAL. That means jump and link. The name of this instruction known to be jump and link, and then followed by procedure label. Procedure label is nothing but here. This is kind of the 16-bit address, like a kind of the immediate format, immediate addressing format, where there is a 16-bit space that is provided for the address of the procedure from where we are calling where the procedure is available and all. So this is known to be like jump and link procedure label and all. Sorry, it's not 16-bit actually. Jump and link actually here this contains the jump addressing mode. So it is it's not 16-bit. It is like the total like 28 bits are used. Oh, not 28 because the opcode will be there 6 bits. The remaining portion entire can be used for the procedure label and all, that address of the procedure label. And here jump and link means actually here this particular statement, this particular instruction, MIPS instruction, will do the two things simultaneously. It means that actually here when you're calling when you're moving to the new procedure, first of all, we should know about the where that procedure is available. That means the address of the procedure is required. So that will be given by this procedure label and all. And jump and link means actually the meaning of this is that, so it will jump to the procedure where the procedure starting is available, the instruction is available. And then at the same time, while doing that, it also stores the PC plus 4. Right now, in the main program, you are pointing to, you are executing JAL, you are executing jump and link instruction. That means you are about to move the control to the new procedure and all. Then once that procedure has to be over, again, you have to return back to the next instruction, that is PC plus 4, right? So therefore, that PC plus 4, that means the next location where the return has to, the control has to be returned back after the procedure has been completed. So that particular address will be placed in a register. That means known to be REA. So this jump and link will do the two things. One thing is that actually it specifies the address of the procedure where the first location or the first instruction of the procedure where it is available. That address will be there. And at the same time, it also places the PC plus 4, the contents of the PC plus 4 value will be placed in a register REA and all. So this is what by using this you can able to you can call the procedures from a main program or from any program you can call the procedures and all. So these are the two things that happens here. That means here it specifies the label of the procedure is nothing but address of the procedure, and also at the same time while moving it also stores the contents of PC plus 4 in the register REA and all, right? And then after that, once the procedure is executed, for example, because whenever you call the jump JAL instruction JAL, it means immediately the control will be moved to the starting address of the procedure. Then the procedure starts execution. That means the PC will be loaded with that procedure label and all. Then after that, the instruction that will be fetched will be the starting address of the procedure. Then the sequence of those instructions in the procedure will be like executed one after another. So whenever it reaches to the last instruction, so the last instruction of the procedure is happens to be this one. Like any procedure call will be JRRA. JRRA. It means jump to the jump to the address specified in this particular register and all. So that means at the end of a procedure written, so use the jump register jump register MIPS instruction. So with that, so what it means is that actually the PC will be loaded with the contents of this register and all. So what is the contents of register? That is the next instruction in the main before calling the procedure and all. So that way you can able to return back to the main program and all. So that means copies ARIA to the program counter and all. And this similar statement can also be used for jumping to the locations where if you want to have a far jumps are required. So in that case, we can use this particular register and all. That means can also be used for computed jumps. Like in case of case and switch statements, also we can use that one. Like because case and switch statements mean there are several alternatives will be there, and then you need to move the control to the specific alternative based on the value whatever you will get. So in that case also we can use this particular register and all. Right. Now let us see just one very simple example of a procedure call. And here the name of the procedure will be leaf example because the reason the name is that like this procedure, this call just nothing but just is a small piece of code, just the sequence of instructions, and then after that it returned back to the main program. And suppose if the procedure contains the nested calls, so that's why here the name of this program, the name of this procedure is given the leaf example, indicating that there is no further calls involved in this particular procedure and all. So here this procedure, very simple procedure, which contains just a single statement. This is just to illustrate how to call a procedure and then how to return to the main program. And in that case, what will be the MIPS code? So for that, to illustrate that, this example has been given. Otherwise, just it's a very simple procedure, just to passing some arguments. And within the procedure, you are performing some arithmetic operation on those operands and all. And then you are returning the result of that arithmetic operation to the main program. That's all. Just to illustrate like how you implement the function calls in the MIPS in the machine code and all. For that purpose, this particular program has been illustrated and all. Here there are 4 arguments we are passing. All of them are integer type. And then we are performing this operation and all inside. And then we are returning the result of this operation over here. And here just assuming that these are the 4 arguments. So the 4 arguments can be placed in there are 4 registers are meant for procedure calling. So therefore, since there are 4 arguments, you can place the 4 arguments in these registers, argument registers and all, right? And then here internally we have one more variable you are using that. And for assuming that suppose you are using this variable, that means for using this variable, you can use the register, any of the registers, temporary registers or saved registers. Just to illustrate that here, we are using one of the saved registers to maintain this variable f and all, variable f. And then whatever the result will come, that results will be placed in V0 so that it can be returned and you can able to observe in the main program whatever the result of this f and all, right? And here since you are using S0 here because you are using S0 in this procedure and all. And as I mentioned that if you are using the saved registers in the procedure, you have to save this register first before using this. You have to save this register at the beginning, and afterwards you can use this register for computing this one for placing the result of this one. And then afterwards, when you return the value after that, then the purpose of this S0 is over. Then again you retrieve the previous value, whatever you stored, that you again place it back in the S0 so that the S0 can be used by the previous program. That means the main program and all. So yeah, here just before going to that, just I mentioned that here, this is not to be, as I mentioned, the stack pointer is nothing but just maintains an address and all, which indicates the location, a particular location and all. And here the stack pointer, if you want to load the data into the stack, into the memory, so the stack pointer, what it will do is it will provide a space. That means it will decrease the, here the stack pointer will move downwards. That means here, suppose you want to create, you want to load a particular register, means content means 32-bit means that you have to create a space for that. That means you have to create a 4 bytes of space. Then in that space you can able to load the contents, whatever you want. So likewise here at the beginning, the stack pointer indicates at the top location of a memory and afterwards, whichever you want to load it into the stack in the memory, then the stack pointer will be decremented. Usually here, from the like a convention, the stack pointer will be decremented. That means stack pointer address will be placed at very highest location, and after that, whatever you want to load it into the memory, then the address will be decremented. Like for example, the memory location is 10,000 was fixed to the stack pointer and all. Then suppose you want to load one register content, 32-bit address, 32-bit data. Then the 4 bytes are required for that. So the stack pointer will be decremented from 10,000. It will make to 9,996, and at that location it will place the register. And again you want to place one more register, for example. Then again you have to further down the stack pointer by another 4 bytes. Then you have to place that. So always the stack pointer places locate the top of the stack, where whatever the recent variable or recent data that was loaded points to the stack and all, points to the stack pointer address and all. So that way it is a dynamic and all. So whenever you are loading the data into the stack and all, the stack will be decremented and then the values will be placed into that. And then suppose whenever you are retrieving the data, whenever you are popping out of the data from the stack. Yeah. Yeah, I think, yeah, participants, please mute your mic. I think you have forgot, one of you forgot. Please mute your mic. Yeah. So that way the stack pointer, you aware of that in your data structures, in your programming and data structures, you use the stack data structure and all. It always places the top of the stack. That means here, whenever you want to load the data into that, the stack pointer will be decremented and you place the data into that. And then whatever the recent item you have placed into the stack, so that is pointed by the stack pointer and all, right? And then whenever you want to pop out, actually the stack pointer will be incremented and all. You have to remove the data from that, and then you have to increment the stack pointer so that that means the stack pointer moved to the one location up. Like for example, 10,000 is the stack pointer original location, and you want to add 2 data items, 32-bit. Then what you do, the stack pointer will be decremented by 8 bytes. So that the 2 locations are available. Now you can able to place it, the 2 items into that one. That means at the 0th location and at 4th location you can use it. And then afterwards, for example, you completed the procedure, your work is completed. Then you don't need those 2 variables. Then simply what you can do is that stack pointer is now updated, then increment by 8 bytes, so that it just now the stack pointer will be again go back to your 10,000 and all. And it automatically, whatever the earlier contents are there, they will be, they won't be there, even though they may be there in the memory location, but the stack pointer now looks at only the top of the stack. That means now at 10,000. So that way you can use the stack pointer. Like originally, initially you can see that the figure A, it shows that the initial one where there is nothing is loaded to stack pointer, that is the location. And afterwards, now the stack pointer is like loaded with the data like T0, T1 and S0. So, and here the way the data is loaded is first T0 is loaded, then afterwards T1, then T0, then S0. So S0 was recently loaded. So the stack pointer with the 0 offset indicates the S0, and the stack pointer with +4 offset indicates the T0, and the stack pointer with +8 offset indicates the T1 and all. So that way you can able to like access the data items from the stack and all, right? So again, after the procedure is over, then you don't want these registers and all, then you can simply the stack pointer will be again incremented by 8 bytes so that it can able to like come back to the original position and all. So that way the stack pointer can be used. And as and when the data keep on added to the memory and all, then the stack pointer will be moved downwards and all. It's a kind of a dynamic one. So with that, there's a problem because since the stack pointer is keep on growing and changing depending upon the usage of the variables or the data that is used by the procedure and all. So therefore, here the stack pointer location is a dynamic. Sometimes it will be at some location, afterwards it may be some other location. So therefore, it is a dynamic. It is dynamic. So with that stack pointer, if you want to access a data item from the stack, it will be difficult because the stack pointer points to the top of the stack, but it's a dynamic. It varies. Suppose you load, sometime you load some 10 items and afterwards you remove the 3 items from that and then now again add 2 items. So that way the stack pointer is dynamic, and if you want to access the data items within the stack, it will be difficult to making use of the stack pointer. By using stack pointer, accessing the data items will be difficult. If you have few items, then you can do that. But if you are multiple items, there are many items are there, and in that case, as the stack is dynamic, it's keep on moving up and down, then difficult to access the items from the stack pointer and all using stack pointer. So that is the reason that we use one more register known to be frame pointer. So the frame pointer is nothing but for every procedure, the frame pointer is defined along with the stack. Initially, both stack pointer, frame pointer may points to the same location. And afterward, the stack pointer keep on moves. If you want to add data, then the stack pointer will be decremented, and then it provides the space so that the data will be added up. And then if you want to remove, then stack pointer will be removed. So that way, the stack pointer, it is like a kind of a dynamic thing. And with that, if you want to locate the different items, so it will be difficult. It will be difficult to track, or it will be difficult to index the various items using a stack pointer and all. So that is the reason that we use the frame pointer, where for every procedure the frame pointer is defined, and then the frame pointer contains the starting address, and then this is fixed. It will not change at all. So therefore, using a frame pointer, you can able to easily track, easily index the different variables or the data items within the stack and all. Whereas the stack pointer is dynamic, so therefore you can't use the stack pointer for locating the various items and all. So this is the way, like a frame pointer, stack pointer, and then here. So this way you can use the frame pointer along with the stack pointer. Yeah, right. So this is the like the previous one, whatever the code I have mentioned, C code, simple C code. You are calling a procedure, and it takes the 4 variables as arguments, and you are performing some arithmetic operation and you are returning. So for this simple procedure call, if you translate that into the MIPS code, and the corresponding MIPS code is like this. Right, a simple one. This is a very straightforward case of that, because you want to, first of all, you are using S0 for holding the F value. That means the result of arithmetic operation. Since you are using S0, we need not use S0, just to illustrate that for if you want to use the saved register, how to save it in the stack and all. For that purpose, it is illustrated. Otherwise, since it is only one variable, you can use the temporary variable itself. So that it need not be saved also. But just for illustrating purpose, I just mentioned we are using S0 register and all. Since you are using S0 register in this procedure, so first of all, the contents of S0 has to be placed in the memory and all. So for that, what we are doing, so we are making a room for that saved register to be placed and all. So therefore, the stack pointer will be decremented by 4 bytes. And now in this location, you are placing the this one, the S0 value and all. Like the S0 value will be stored, right? Store word in the at the stack pointer with a 0 offset, because the stack pointer is decremented now at the top of the stack location. You are placing this S0 value and all, placing the S0 value. So now S0 is stored, right? The previous value S0 is there in the memory and all. Then afterwards, you can use S0 for the local calculations. So here, we have the 4 arguments A0, A1, A2, A3 are there, and then the operation to be performed is that you can see here, this is the operation G plus H minus I plus J. So all these G, H, I, J are available at the 4 argument registers and all. You can use them directly. You can use add where the G plus H can be carried out, A0 and A1, and you can use another add for carrying out the other summation. Then you need to perform the subtraction between these two. So that's what subtract instruction T0, T1 will be done. And the result of this is placed in S0. Since you are using S0, that is the reason that the first two instructions are meant for storing the S0 and all. Suppose in place of S0, if you use T0, for example, then there is no need of these two instructions and all, right? Just for illustration, we have kept these additional instructions and all, just to illustrate if you want to use S0, then how to like what will be the procedure and all, right? And then the S0 is there, and then S0 now contains the F value. So this S0 has to be placed in V0. S0 has to be, the contents of S0 has to be moved into another register V0 and all. So for that, we can use, instead of there is a move, there is no separate move instruction is there. In place of that, we are using the add instruction itself. Add S0, comma 0. This 0 is nothing but zero register. It always holds the 0 value. And then the result will be placed in V0. So that way, the add instruction can also be used for moving the register contents among themselves, right? So this way you can use this one. So now the result is available at V0 and all, right? So then the job of this S0 is over. So therefore, again, wherever the S0 is stored, so that S0 will be again recovered, again restored and all. So that the 0 SP, like where the S0 is and the top of the stack pointer, the S0 is available. So now you are loading back to the S0 register. Right?
Hello, sir.
And after that, after reloading back to the S0, now the S0 contains the previous value and all. Then the S0 job is over. So therefore, again, you place the stack, you again readjust the stack to original position and all, because this S0 is not required now, right? So therefore, now SP to SP plus 4, right? So that the stack will be again come back to the normal position. And then after that, this is with that the procedure is over. Then the last statement of the procedure will be GRRA, because we know that at the beginning, when you are calling the procedure, at that time the next instruction address is placed in RA and all. So now by using this, now the PC is loaded with the RA, so that it's nothing but the control is shifted back to the main program and all. And now the registers V0 contains the result of that, so that the main program maybe later it can use the contents of V0 for accessing further. So that way you can use you can call the procedures from the main program, and this is the corresponding MIPS implementation for that. Okay. Yeah, then yeah, for a non-leaf procedures means actually this is a simple procedure call. Just you are calling a procedure and then the procedure is executed and then coming back. The similar thing can also be holds good for a non-leaf procedures also. Non-leaf procedure means you are calling a procedure and that procedure will in turn call some other procedure and that may call some other procedure. So likewise, the calls may exist with the nested calls, or recursive calls may also be there and all. So in that recursive calls, you need to take care of following, because if it is a single call and again you are returning back, then immediately the return address will be there in RA. And again, the procedure, whatever you have called, that is calling some other procedure. And then that again calls some other procedure. So in that case, to again come back to the normal thing. So what you need to do is that the return address, whatever is there, that has to be placed in the stack. Whenever you are calling the next procedure, the return address has to be placed into the stack. And along with the return address in this procedure, whatever the variables you are already used, and if you want to use it further later on after this function call, that those are also has to be placed into the stack pointer and all. Then you can then you can go for calling the next call. And again, in the next call, again, you are calling for some other call again you have to do the same thing. The return address, whatever is there, so that has to be pushed into the stack. And then similarly, the arguments also, whatever that are used and they can be used later, they also be placed into the call, placed into the memory and all, using a stack pointer and all. And then afterwards, when you are returning back successively, appropriately, you can recover you can able to restore the contents and all. You can able to restore the content. Right, this one you can able to visualize using this non-leaf procedure. Just a simple code corresponds to factorial, evaluating the factorial of a number and all. You can do it either iteratively using loop. With the loops also you can do that, and the same thing can also do with the recursion also. So this is the recursion procedure call and all. And here in this recursion procedure call, you had to like suppose assuming that the n whatever the factorial you had to compute put it in one argument register and all, then the result will be in v naught because you will get only one end result, this v naught. But this is a recursive procedure call, then this is the code for this recursive procedure call, because here you can see as per the recursion, first you are taking a value of n, then you are checking whether n is less than 0 or not. If it is not, then again you are decrementing the n and again you are calling back recursively and all. So this is the corresponding code. You please go through that carefully. It's a very simple one, but when you're going through that, you will come to know that at several times you are storing into the stack. Suppose that depending upon the n. Suppose if n equals to 10, almost like 9 times you are storing the return address and all, because 10 means you are calling the factorial 10 times, right? So each time you are storing something into the register, something into the stack and all. Then after you reach to the end of the call, then you are trying to recover the data that is there in the stack, like a step by step, one after another and all. So those things you can able to see that using this particular MIPS like instruction sequence of instructions. So please go through that carefully. If you take some example, then it will be clearer to you. Take n equals to 5 and then see that how the control is moving across these statements and all, right? So please go through that. I'm not going to explain now here. Yeah, the next thing is that actually here when you are loading the like a program into the memory and all, there are different things that are happening here. First of all, actually, when you write a code, then suppose when you write a code in high-level language, then afterwards the compiler will take care of that for deriving its machine language. Compiler then followed by assembler and all. Then the assembler usually like the assemblers first they will make use of the convention of addressing the different segments over here and all. Like here, suppose assuming that we have certain memory, main memory and all, like you have certain memory size is there. And in that, the bottom of the memory will be reserved for actually the operating system and some basic system programs will be reserved at the bottom of the memory and all. Then afterwards, the user programs will be loaded over here and all. Afterwards, the user programs will be loaded here. And in that also, like in the user program also, the way the program will be loaded will be first thing is the text segment will be loaded. Text segment is nothing but the instructions of the machine instructions in the binary format. That is not to be text data or the instructions directly in the binary format. Then afterward, the static data. That means if the program involves some constants or some static variables or constant arrays or so those are all comes under the static data and all. So those data values and all of them will be placed in the above the text segment and all, above the text segment. And after that, you have and these the procedure the whatever the application, this may be calling some procedures and all, and for execution of the procedures and all, so you for a local procedures you make use of the stack. That means whenever the procedure is called, then immediately the corresponding arguments, the local data, all of them will be stored in a stack, and then the procedure will be executed with the help of the data that is maintained by the stack and all. And along with that, there will be some data. Sometimes the data will be of a dynamic nature and all. It means that, for example, suppose if you store the data in the form of linked list, then when you are manipulating that, the linked list size may be grow or reduced. So that way, this kind of data is known to be the dynamic data and all. It means that the data can grow up and can grow, and sometimes the data size also will be reduced. So here for these dynamic data and this the stack will be indicated by like a stack is like pointed by the highest memory location, and the dynamic data will be after allocating some space for static data. There will be some address will be given for the starting address of the dynamic data and all. And here from this starting address, the dynamic data will grow as per the requirement and all. Similarly, the stack also as per the procedure, the number of local variables or the data, local data, whatever is required. So with that, the stack also will move. Here the stack will move downwards from highest address to the lower side. And whereas this dynamic data, for this, the address will be moved in the upward direction. And here the data structure that is used for maintaining this dynamic data is known to be heap bundle. So the heap in the heap, the data will be moved, or the heap size will be increased in the incremental way, like with the address is increased in the increasing direction. Whereas in case of a stack, the address will be the growing stack is nothing but address is moving towards the lower side and all. So that way these are free to move like up and down, and so that way this total space can be effectively utilized by these two data structures and all, stack and as well as the heap and all. So, and here one more thing, as I mentioned, a global pointer is nothing but it used to like index or locating the data items within the static data. That there is some static data segment where the values are either constant or constant arrays or strings, whatever is there, all of them are placed in the static data. Like it will be like within certain memory addresses and all. So to access this static data, we use the global pointer. So the global pointer, what we do is suppose the static data is from like 100002, like for example, 1000 followed by triple F. There is a hexadecimal code. And usually the global pointer will be placed at the middle and all. The global pointer is nothing but it's a register which holds the mid part of the mid location of the static data segment and all. And with that, actually, by using appropriate offset, either positive or negative offset, you can able to access the static data segment. It is nothing but various locations in the static data segment. So that way the global pointer is meant to access for static data, and the stack pointer is meant for like accommodating the space for the local procedure data and all. And there is another pointer, as I mentioned, frame pointer. The frame pointer is meant for, it's a fixed one, and with that you can able to locate the data items in the procedure, local procedure and all. So that way these are the three pointers, like the three registers which holds the specific addresses and all. Right? Yeah, right. Okay, so these are the various registers and all what we have used in the MIPS so far. You can see there are total 32 registers. And so these are the different naming conventions that are used in assembly code, like in a symbolic language. And their actual codes are this one. Like when you are translating these names into the machine code, then these are the numbers that are used 0 to 31, right? And so this is the purpose of the specific registers and all. Generally, they will be used for this purpose. And here there is register 1 is missing. So this register 1 is used by the assembler, basically. Register 1 is basically used by the assembler and all. That means after compilation, the assembler will do certain activity. It means that sometimes the compiler will use we'll use some symbolic code or symbolic instruction, which is not part of the actual machine instruction and all. For example, say that you have like, for example, moving the contents of a data from one register to other and all. So in that case, for the sake of simplicity, the compiler will simply use some instruction, some symbolic instruction, say that MV, comma R1, comma R2. It means that moving the contents of R2 to R1 and all. But that actual instruction as it is not available in the machine language or in the instruction set and all. Whereas the same thing can be implemented by using add instruction and all. So these kind of translation of the instructions in the symbolic form, which are not part of the actual instruction set, will be translated back to the set of the corresponding instructions of the instruction set is carried out by the assembler and all. So in that process, the assembler will make use of this particular register and all, register 1. So this is known to be like assembler register and all, 80. And there are two registers again. There are two missing here, 26 and 27. So they are not mentioned here and all. So far we are not come across those registers, usage of those registers and all. So these registers are usually used by the operating system and all. So they are not used by the compiler and all. So they are used by the operating system and all. So that way there are total 32 registers, and these are the purpose of the various registers. You can see. Yeah, then the next one is that so far we discussed about mostly the data that we handled with the 32 bits directly. right? And sometimes actually we need to access the data like at byte wise, at a byte wise. But most of the time so far, whatever most of the cases what we dealt with is that, so whenever you are fetching a data from a memory or whenever you're fetching a data from a register, whatever, it's always the 32 bits and all. But as we know that, suppose if you want to manipulate the strings or manipulating the characters or text data, for example, so far as and when the other data, like in case of arithmetic operation, all these things we use the 32-bit data. Suppose there is some kind, sometimes no, you need to, there are some applications where we need to process the text data, need to process the text data, right? Text data means alphanumeric data, this alphabet data which contains alphabets and other things. What suppose English language, for example, is a text data. So you want to process the text data, you want to do some manipulations on that, or your application program depends on the text. You usually uses the text data, for example. So in that case, if you want to use the text data or manipulate text data, then the programs requires instead of word level data, you require like the subword level data. That means the half of the word or one quarter of the word and all. So why that? The reason is that because if you want to process the text, the alphabets has to be coded by using certain specific codes and all. So therefore, for accommodating the whole text and all, you can have already some coding schemes already there. Known to be one is the ASCII representation. So with that, it can able to accommodate 128 characters. So in that 128 characters, 95 are the graphic and 33 are the control characters. So we have all of you have come across these ASCII code representation for representing the alphabets, or small or capitals and all, and different symbols also we represented by using ASCII code that we come across in the first year itself. Likewise, there are different representation. There is some Latin one representation where it provides a 256 characters and all. Provides 256 characters and some of the graphical whatever. And now recently we are using entire 32 bits for representing the characters and all. So here the reason for this is not to be Unicode. The reason is like a universal representation of all characters and all. So this is because the 32-bit represents a vast space. There are several representations can be possible because if you use the ASCII, only 128 characters are represented. It means that only 7 bits are used, 7 bits are required. Whereas the Latin 256 characters means with 8 bits you can able to accommodate all these 256 characters. So whereas Unicode we used to represent 32 bits for representing a character because it it caters the representation for characters of the universe, all the languages that are present in the universe and all. So that way it uses a 32-bit character so that all characters like either the characters in English or characters in Indian languages or characters in any of the other representation also can be used, can be accommodated using the Unicode and all. Right. So now we just focus on the ASCII and all because it's the general format that is used for manipulating the text and all. And in case of ASCII, these are the coding scheme for ASCII, just representing the ASCII value and the corresponding character and all. You can see that this is the corresponding character. It's represented by with a specific ASCII value and all, like 32, 33, and so on. This way and so on. Right. So you can see that the numbers you can represent some symbols, mathematical symbols, different other operators. You can see that and alphabets in small and capitals. So all of them you can able to represent by using this ASCII code. Like there are total 128 bits can be used, and so with that you can represent that. And now, if you want to perform the text data, for example, you can see that in your C programming you had done the string manipulations like copying the string or finding the length of the string and all. How do you do that? You have a string, you know the string and all. You are fetching each character, and then you are counting that. Suppose, for example, you have a word where in that a word contains the 5 characters, for example. How do you do that? You just fetch each character, character by character, and then you count that, how many characters are there. Likewise, also, when you want to check the word with some other word, whether the two words are equal or not, what you do, you just fetch the character by character and then perform the equality operation. If all the characters are equal of one word with the other word, then you can say that both words are same. Otherwise, they are different. Something like that. There are lots of string manipulations are required in several applications and all. So in that case, there is no need for like like fetching the 32-bit word and all, because the characters are represented by, in case of ASCII format, the character is represented by byte, 8 bits. 8 bits represents a character and all. So in that case, if you want to do the character manipulations and all, we need to manipulate, or we need to handle the data at a byte level and all. So for that, to accommodate that, the MIPS instruction set also supports the byte and half word as well as a word. Words, so far we have already come across like a load word LW that indicates the load word. It means it fetches the entire word, 32-bit word, starting from the given address. Like all 4 bytes will be fetched. And here, correspondingly, here we are here LB means it just fetches the byte. It just fetches the a byte. That means 8 bits at this, because we know that the address, the entire memory is byte addressable, right? At every byte there is a unique address is there. So with that you can able to load the specific byte, whichever is given the same format, offset. Then RS is the base register. Then this is the offset. It provides you the actual byte location, and at that location, whatever the 8 bits are there byte, so that byte will be transferred to RT register RT and all, right? And similarly, this is LH. It's nothing but half word. You are, instead of byte, 2 bytes you are transferring. 2 bytes you are fetching at this location to the RT, right? But you are putting back into some register, but the register contains the 32 bits, right? Register contains the 32 bit. Register length is 32 bits. So, but here we are fetching only word, 8 bits, or here we are fetching only half word, that is 16 bits. So we'll place this 8 bits and 16 bits in the rightmost place of the register, because the register contains 32 bits, right? In the rightmost 8 bits or rightmost 16 bits are filled up with the this one, the half word or a byte and all. And the remaining bits are filled up with the zeros, extended by 0 and all. Remaining bits are extended with zeros and all. So that way, the entire 32 bits will be filled up, where the desired byte will be the actual information, and the remaining will be simply zeros. Likewise, if it is a half word, the 16 bits will be your information, and the remaining 16 bits will be the simply zeros and all. So that way, you can use the registers for capturing the like a word byte, even the words are half words also, right? And similarly, store also, storing the same thing. Like, so when you're storing means what you do, but here for storing, that the convention, the format will be, you have to take the contents from the register and you have to store it into a memory. But the register contents are 32 bits. So therefore, again here, for storing purpose, suppose when you specify the store byte, it means that it just take the rightmost byte of the register, because the register is 32 bits, it is 4 bytes. So therefore, whatever the rightmost byte is there, that byte will be picked up and it will be placed in the desired memory location and all. Likewise, the half word also, right? And this is the example of how the string copy can be carried out. With a simple example, it's very straightforward. You can nothing explanation is required. So for whatever we have done, so with that itself, you can able to understand very clearly. Just as a function call, 2 arguments, arrays, and then you are performing that copying, like from one string to string y to copying to string x and all. And here x and y are the address of x and y are placed in a0 and a1, right? And then you can able to access. And here I is the one that is used in the procedure and all. You can use either temporary register or stored register. Here it uses stored register and all. So then accordingly, this was the code for that. Since you are using stored register, stack point is decremented first. These first 2 steps are for retaining the stored, placing the preserving the stored register and all. Then afterwards, the sequence will be just, it just follows the sequence here and all. Okay, so we'll stop here at this point, and maybe we'll continue this in the next class. Mostly maybe another 15 minutes will take for completing the rest of this, and afterwards we'll move on to the arithmetic circuits and all. That means the design of ALU, multiplier, division and so on. Yeah, we'll stop here. Let me. Okay, yeah, let me stop the recording first. Okay.